Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to discuss the final tutorial for chapter 5 hydrocarbons with 9 our 3 non-face-to-face questions. For question 1, you need to predict the product formed from the following reactions. So we have already learned a number of reactions under alkene. So we are going to apply the knowledge that we have already learned in these reactions. So take note that we have this alkene. So our alkene now has the parent chain of 1, 2, 3, and 4, 5. And then we have one branch in here because we have these parentheses. So we're going to react it with HBr. Note that we got nothing on our arrow, means that they are conducted in inert solvent. So the species that is going to be added to this alkene is the H and also Br. Note that Markovnikov rules suggest that in additions of the HX, they need to follow the Markovnikov rules. The hydrogen will be added to the carbon with more hydrogen atoms. So between the carbon in carbon-carbon double bond in here, which of those going to have more hydrogen on it? So we could see at carbon number 2, they got more hydrogen on it. So the H will be added to that particular C, while the Br will be added to that particular carbon number 3. So we're going to rewrite the structure here by eliminating one of the double bond. We're going to add our species H and also Br. So H will be added here, while Br will be added here. That follow the Markovnikov. Next, for B, we have exactly the same HBr to be added, but this time around we have the presence of these hydrogen peroxides. So whenever we have HBr or HX with the presence of hydrogen peroxides, means we are going to disobey the Markovnikov rule, means this reaction will follow the anti-Markovnikov rules. Instead of hydrogen, will attack the carbon with most number of H. Now the Br going to attack the most number of carbon with most number of H, which in this case the carbon number 2. So we are going to get the product that is opposite to the other reactions. So now we're going to eliminate one of the double bond in here, the multiple bond. Now we are going to add this Br at the carbon with more hydrogen atoms. So Br will be here, while the hydrogen will be here due to the hydrogen peroxides present. Next for C, we have this alkene react with 1O3, and the second condition is zinc and H2O. So if we look carefully at these solutions and also conditions, we know that these reactions is involving the ozonolysis reactions. So we know that ozonolysis reactions will involve the oxidative cleavage, means we are going to cleave this bond and simply insert the O. So now we are going to cleave this bond and we are left with 1, 2, 3, 4, and 5 carbons. So we are going to write the 5 carbons. So 1, 2, 3, 4, and 5. At carbon number 3, we're going to have the double bond. So at this double bond, we're going to simply insert the O. While for the other carbons on the right hand side, we have 1 and 2. So we're going to add these 2 carbons. So 1, 2. And at the first carbon, we are going to put the double bond O. So we're going to have a combinations of ketone and also aldehyde from these ozonolysis reactions. As for D, we're given cyclohexadiene to react under the conditions of hot acidified cheminophore solutions. How do we know this? By looking at the conditions given in here. So this is another oxidative cleavage of carbon-carbon double bond, just like in ozonolysis. But this time around, it's a bit different from the ozonolysis. After we have cleaved the bond, we cannot simply insert the oxygen to the carbon-carbon double bond. We are still going to cleave this bond and then we need to look at how many hydrogen attached to that particular carbon that being cleaved, because the product will depend on the hydrogen attached to the carbon. So now we have in here, we have one hydrogen. In here we have one hydrogen. This got one hydrogen, and for this carbon we got no hydrogen, and the other one we have one hydrogen. So we have already learned that if we have no hydrogen attached to the carbon, means we are going to form ketone. If we have at least one hydrogen attached to the carbon, means we are going to form carboxylic acid. And lastly, if we have two hydrogen attached to the carbon, means we are going to form carbon dioxide and water. So by cleaving the carbon-carbon double bond, we are going to get a carbon chain that include these 1, 2, 3, and 4 as the longest chain for the first part. So means we are going to write the 1, 2, 3, and 4. And look at carbon number 2. So the carbon number 2 going to be here. So carbon number 2 got the double bond, means your double bond will be, one of them will be here, and another one is at carbon number 4, means we have double bond in here. Just now we say if we got no hydrogen attached to the carbon, means we are going to get ketone. So simply insert the O here. And then for the fourth carbon, we have one hydrogen attached to the carbon, means we are going to form carboxylic acid, means we're going to have this as OH, while this double bond will take one of the oxygen. So this is going to be our product for the first part. But this is not the final product because we got another part of carbon down here. So now look how many carbon do we have? 1, 2, 3 as the longest chain. And then at carbon number 2, we have one methyl group. So we're going to rewrite this product. So we have the longest chain of 3, 1, 2, 3, and we have this methyl group. We cannot change the structure because this is the carbon chain that we included in the initial structure. Look at the first carbon. We have the double bond. So we need to write the double bond. And also the third carbon, we have the double bond. And then look at the hydrogen attached to each carbon. We got one hydrogen, means that we are going to form carboxylic acid on both sides. Like this. So this is going to be your final answer for D. For question 2, we are given alkene X produces ethanoic acid. So ethanoic acid is carboxylic acid with 2 carbons, and also butanon. Butanon got 4 carbon, and on it we have carbonyl group. So this is going to be our structural formula when reacted with hot acidified KMnO4 solutions. So we are given only the product. Now we need to predict the structure of the reactant itself, the alkene X. So we have done these reactions earlier in the previous questions, where we have the KMnO4 H plus and also heat to form this kind of product. So we have CH3 C double bond O OH. So this is our ethanoic acid together with the butanon. So we have CH3 C double bond O CH2 CH3. So simply follow the structural formula given in the questions. Now, we want to predict what kind of alkene X has been used to form this kind of product. First, we need to check that our alkene gonna have a total of 1, 2, 3, 4, 5, 6. So, we know that these reactions that include the oxidative cleavage of alkene, we are going to cleave the carbon-carbon double bond to get the carbon double bond O. So we have that one hint, means that we are going to combine these two products together. But then, look at the product form. If we have one hydrogen attached to the carbon, means we are going to form this carboxylic acid. So we know that at this carbon with double bond O, we're going to have only one hydrogen. And for this butanone, since we are going to form ketone, it means that we are going to have 0 H on the carbon-carbon double bond. So now we are going to combine these two. So let's say I'll take this structure. Okay, I'll just copy them and bring it here. So we have this carbon chain, and then we're gonna combine it with this. So make sure you are going to combine them at the right place. So it should be in here. So let's just alter a bit. So we know that the carbon-carbon double bond will be between this carbon and this carbon. Look carefully. The carbon with CH3 here, so we have the double bond. And then here we have the second carbon here. So knowing that this is going to be your product, don't forget that we have this indicator that this is 1H attached to the hydrogen. We need to check that the carbon is bonded to 4 substituents or any other atoms. And then yeah, so this is going to be our alkene X. So if we have to give name to this compound, then we need to check for the longest chain. So your longest chain gonna be 1, 2, 3, 4, and 5. So this is gonna be pentene. So we have pent 2 in because the double bond is located at carbon number 2. And look carefully at carbon number 3, we have methyl group. So we're gonna have 3 methyl pen2-ene. So this is gonna be our alkene X. I'll zoom this a bit to make it more clearer for you to see. So I'm gonna resize this. So yeah, so this is gonna be our alkene X of 3-methyl pen2-ene. For question 3, you need to outline the synthetic pathway for the formations of 1,2-dibromocyclopentane from bromocyclopentane. So when we say synthetic pathway, it is not the same as the mechanism. It's just a pathway that may require more than one solutions and also conditions to be used in order for you to get from reactant to products. So in order for you to answer this kind of questions, we need to first draw the structural formula of the reactant given. So we're going to start from the bromocyclopentane. So we have cyclopentane as the parent, and attached to it we have one bromo. And then we are going to form this 1,2-dibromocyclopentane. So again, cyclopentane as the parent chain, and now we have 2 bromo attached to this cyclopentane. So you are free to choose whether you want to put the Br at this carbon or maybe the other neighboring carbons. Alright, so please have a look at this initial structure. You are going to start with alkane, and then your final product is also alkane. From what we have learned, we only have 2 reactions for alkane, which are halogenations and also combustions. Means that we cannot have this product of 1,2-dibromocyclopentane directly from the bromocyclopentane. We're gonna need another way to form this 1,2-dibromocyclopentane. So since we have this haloalkane, we can first form the alkene. How do we know this? By looking at this 1,2-dibromo, means we're going to involve the 2 carbons. So the only class of compound that consists of 2 carbons to be used at the time is the alkene. So we are going to first form the alkene. So maybe you have this alkene here. Since this is haloalkane, we are going to use these conditions of KOH in ethanol under the conditions of reflux. So we are going to form carbon-carbon double bond between this carbon and also this carbon, since we aim to put the Br up here. So then we're gonna have our cyclopentene like this. Okay, and now we are going to add the 2Br from the cyclopentene. So since we want to insert both Br, means we're going to undergo these halogenation reactions. So halogenation reactions that take place in here is in the inert solvent. So we have CH2Cl2 as the medium. So lastly, we'll get this final product of 1,2-dipromocyclopentane. Let's proceed to the face-to-face questions. So question 1, they want you to write an equations of the reactions between 2-methyl-2-pentene. So this is going to be our alkene, and we need to react them with HCl, means hydrohalogenations, and outline the mechanism for the formations of product. So we need to first write the alkene given in our reactions. So we're going to have 2-methyl-2-pentene. Our longest chain going to be 5 carbons. So 1, 2, 3, 4, and 5. At carbon number 2, we have methyl, and also at carbon number 2, we have carbon-carbon double bond. So this is going to be our 2-methyl-2-pentene. And then we're going to react this alkene with HCl. So hydrohalogenations, since we got no other solvent given in here, means we are going to dissolve them in inert solvent. And lastly, you will get the product of H and Cl be added to this alkene. So means we are going to do these electrophilic additions. So again, if we have HX added to the alkene in inert solvent, means the hydrogen will follow the Markovnikov rules. They are going to be added at carbon with more number of H, which in this case, the carbon number 3. So carbon number 2 is the carbon that the Cl gonna be added. So we'll write this structure again. So 1, 2, 3, 4, and 5. And then don't forget the methyl in here. Then we are going to add the Cl at this carbon. So Cl. And at the third carbon, we're going to put H. So we don't need to show this H, but for this time, I'm going to show it to you so that you can see more clearly the difference between these two carbon-carbon double bond. Alright, so from these general reactions, we're going to write the mechanism involved for the formations of product. For hydrohalogenations, we're going to involve 2 steps. The first step is going to be formations of carbocation. So how are we going to form this carbocation? By attacking this nucleophile towards the electrophile. So we need to first emphasize who's going to be the nucleophile. So this alkene going to be the nucleophile due to the carbon-carbon double bond that reach in electron, while HCl will become the electrophile. So in the first step, the carbon-carbon double bond will break, and then one of the carbon will attack the H and take them in, while the other carbon will become the carbocation. So now this double bond will react with the HCl and make sure to show the bonding between the HCl because we're going to involve the bond breaking. So from this rich in electron species, we're going to take these hydrogens, and since hydrogen is a duplet, they cannot form 2 bonding, means they're going to break this bond. So from here, we're going to get a product of, so we have 1, 2, 3, 4, and 5. Don't forget the methyl. So hydrogen will be added to the carbon with more hydrogen on it. So means that this hydrogen going to be added here, given this carbon will become the positive charge because they lose one of the electrons comes from the carbon-carbon double bond. So when we have carbocation, we need to look for the possibility if they can form a more stable carbocation. So at the moment, we have a tertiary carbocation due to the 3-alkyl group attached to this carbocation. If we happen to move this carbocation to the neighboring carbons, let's say to the left, means we are going to have primary carbocation. If we want to do some hydride shift to the neighboring carbon on the right, means we're going to have secondary carbocation. So if we got no possibility to make it more stable, then we should stay as it is. We don't need to do the rearrangement process. So we'll have these carbocation as the most stable carbocation since they are attached to tertiary to the 3-alkyl group, means it is tertiary carbocation. Alright. The second step gonna involve the nucleophilic attack. So we're gonna write the step 2 as nucleophilic attack. Nucleophile means the one that has more electron on it. So initially we have our carbocation. So this gonna be our carbocation here. So now we are going to attack this carbocation with the nucleophile. So the nucleophile that we're talking about is the Cl minus, comes from the HCl being broken just now. So this is going to be our Cl. So this Cl got more electrons on them. They are going to attack the carbon with less electron on it. So means the carbocation. And lastly, we're going to get a product of 4, 5. So the Cl will goes here, as suggested by our general reactions. For the next questions, you need to outline the mechanism of the reactions between 2-methyl-2-butene with acidified water. So we need to first draw the structural formula for this 2-methyl-2-butene. So we're going to have the longest chain of 4 carbon, 1, 2, 3, 4. At carbon number 2, we have methyl group and also the carbon-carbon double bond. So this is going to be our 2-methyl-2-butene. With the reactions of acidified water, means we are going to react them with H2O in acidified conditions. So we're going to have H plus or H3O plus. So let's say I have this H3O plus. Then these reactions going to add the OH and also H. Since we have the combinations of 2 species to be added, means we need to look at them if they are going to follow Markovnikov or not. So since we have hydrogen, means they are going to follow the Markovnikov by adding the hydrogen to the carbon with the most number of H. So now we're going to add the hydrogen at carbon number 3. So this is going to be the H, and also this one going to be added with OH. So we are going to do the mechanism for these reactions. The mechanism for these reactions will involve 3 steps. The first step is going to be the formations of carbocation. Just like in previous reactions, we're going to start with our alkene as the nucleophile. And then we're going to first attack the acidified water, the H plus or H3O plus, because they are more susceptible to be attacked due to the positively charged. Means we're going to have our OH3 in here with only one lone pair, indicate that this is positively charged. So this nucleophile will take the hydrogen first, and then we're going to break the bond here, and by transferring all the bonding electrons to the oxygen, which is more electronegative. So then we're going to get the carbocation at the second carbon. So we have 1, 2, 3, and 4. Hydrogen has been added to this third carbon, means that our second carbon gonna have positively charged carbon. Now, since we have formed this carbocation, look if there is possibility for this carbocation to become more stable. At the moment, we have tertiary carbocations. So this tertiary carbocation is the most stable carbocation. So means we got no other possibility to make it more stable. Let's proceed to the second step. For second step, they will involve the nucleophilic attack. So this nucleophilic attack comes from the water. So the one that we are going to react with. So we are going to attack this carbocation ion with the water. So we're going to write the intermediate form. I will write this. In your exam, you can simply continue from this structure on the right. So I'm going to have this carbocation ion here, and then we'll react them with water. So OH2. So just now from these reactions, we're going to have a side product of water. So please be reminded that the acidic conditions we've used is the acid catalyst, means we're going to regenerate them at the end of these reactions. So this water down here will become the nucleophile, and this carbocation ion will become this electrophile. Means that this lone pair on this oxygen will attack the carbon in here, means they are going to be added to this carbocation ion, forming an intermediate of 1, 2, 3, 4, 1 methyl, and attached to this carbon we have oxygen with 2 hydrogen. One of the lone pair has been donated, means left with 1 lone pair, indicating that the formal charge on this oxygen is going to be +1. So we're going to have positive charge on this oxygen. Now, our aim is to form alcohol, means the third step going to involve the formations of alcohol. Step 3, formations of alcohol, in other words OH instead of OH2. So now, since we have this OH2 regenerated from the acid catalyst, we're gonna have them as the nucleophile. So we're gonna react this structure here. So let's say I'll copy this and then bring it here just to show you once again. So make it slightly smaller, and then we're gonna react them with water. So let's say I have this color. So we'll take this oxygen, hydrogen, hydrogens with 2 lone pair, and then we're going to take one of the H here and break this bond to give you the final product of our alcohol. So we have 1, 2, 3, 4. One of them is methyl, another one going to be the OH with 2 lone pair. So this is going to be our final product from this mechanism. As for the last questions in this tutorial, you need to propose a chemical test to differentiate between pentane and also pentene. So since hydrocarbons covering the alkene and also alkene, we need to use a chemical test to differentiate what's the difference between them. So even if the questions didn't gives you instructions regarding write the observations and also write the reactions equations, whenever you're dealing with questions of chemical tests, then you need to write these two things. They are the format to answer these questions. So we have to write these two things for each of the structure given in here. So we have choices of 3 chemical tests to be used. One is Bayer's test, where we use camenophore, coal, dilute, and also OH minus. And then we have bromine in inert solvent. And then lastly, we have bromine in water. So let's say I'll take the Bayer's test. So I have to name the test. So we have name of test is the Bayer's test. Next, I have to write the reactions equations for both pentane and 1-pentene when reacting with the coal camenophore solutions. So we're going to first write the pentane structure. So 1, 2, 3, 4, 5. And then we're going to react them with camenophore under the conditions of dilute, OH minus, and also coal. Actually, they are conducted at room temperature. And then we're gonna have a negative results of no observable change. The reason why are we doing these chemical tests, because one of them should give you positive, another one gonna have negative results. So that's the only way that we can use to differentiate between these two hydrocarbons. So no observable changes. Now what about the observations? So the observations, since we are using the K-4 solutions of purple in color, so we're going to see that the purple color of K-4 remain unchanged. So that's the first observations for our pentane. Now we're going to proceed with the 1-pentene. So 1-pentene have exactly the same number of carbon as pentane, but this time around we have carbon-carbon double bond at the first carbon. So again, rewrite all the solutions and also conditions given. So we have this dilute, OH minus, cool. Then this carbon-carbon double bond will have a product of diol. So at both carbon involving the carbon-carbon double bond, we're gonna add OH. So let's use red colored pen. So OH and also OH. By having two hydroxyl group attached to these carbons means we are going to form diol. And together with the brown precipitate of MnO2. So usually for precipitate, we use this symbol showing that this is brown precipitate. So we have to indicate them in our reactions equations. So brown precipitate means that in our observations, we're going to have something different from the one in pentane. So our observations going to include 1, the purple color of K-4 decolorized because they are forming a reactions. So they are going to decolorize. And next we have brown precipitate formed. We have to write both observations. Well, if you choose to do the bromine test, then you're going to have different observations where our bromine is reddish brown, means if they can form reactions, means they're gonna decolorize, and etc. Alright, that's all for this chapter. Thank you.